Thank everyone for coming. This is the third of 3 defenses for WinLab today. So far we're 2 for 2. No pressure. The third defense is on a different topic, quite different than the others. It's on a network security topic related to MobilityFirst and future internet design. Xiruo's been working with me on this topic over the past few years. And some of you might be familiar with some of her work, but today she's also going to present something that hasn't been shown to people before. So without further delay, it's all yours.
Thanks for the introduction. Good afternoon, everyone. Thanks for attending my thesis defense. Today, I'm going to talk about my thesis, integrating security and privacy protection into a mobility-centric internet architecture. All of us are familiar with the huge success of the internet. In the early stage, the internet was just a small-scale academic testbed. However, several decades later, it has become a large-scale commercial network that spans the world. It has evolved into a hierarchical architecture and connected lots of different network paradigms. And it keeps evolving. New applications and emerging network paradigms are arising and putting new requirements on the internet infrastructure. For example, mobility is one of the major trends. There has been a large-scale shift from static endhosts to mobile devices. Also, people have concerns about security and privacy. There have been numerous attacks. Xcode Ghost, OpenSSL Heartbleed. The attack list could be very long. In response to those new requirements and challenges, there have been efforts trying to develop new future internet architectures. Here at WinLab, we have MobilityFirst, which centers on the support of large-scale mobility. Also, MobilityFirst tries to address security and privacy issues, as well as accommodate emerging services. MobilityFirst explores and introduces many new network protocols and functionalities. Perhaps the most relevant ones to this thesis are the cryptographic globally unique identifier GUID and its related name-based service layer. I will talk about this in detail later. Now, this thesis uses MobilityFirst as an example to explore several challenges related to security in the future internet. In the rest of the talk, I will go deeply into the work of securing a non-resolution service and the work of a unified MobilityFirst-based Internet of Things architecture. I will also provide an overview of the access control framework as the non-resolution service. In addition, this thesis also explored a lightweight overlay tunneling approach in the MANETs as a means to mitigate network failures and attacks. This lightweight overlay approach can serve as a policy tool and does not require redesign of the underlying network routing protocols. But for brevity, I will not discuss that work in the talk. Now, as a background, let's first take a look at the MobilityFirst protocol stack. To replace the narrow waist formed by TCP/IP in the current internet, MobilityFirst introduces a name-based service layer, which consists of NAND Certification and Resolution Service, Ncrs, and the Global NAND Resolution Service, GNRS. This newly introduced service layer is centered on the concept of flat, security-based GUID for network objects, which serves as both the network object's identifier as well as the public key. Because of the importance of this service layer, we would like to first secure the GNRS. Then, with the secured GNRS in place, we may be able to extend our security protection to the rest of MobilityFirst network. This service layer adopts a two-tier NAND resolution approach. So in MobilityFirst network, each network entity has three attributes. On the top, we have user-level descriptors, which are human-readable names. In the middle, we have network-level identifiers, which are GeoIDs. At the bottom, we have routable topological addresses, which are network addresses, such as IP addresses. And the two core NAND services provide translation among these three attributes. The Ncrs provides two-directional translation between the human-readable names and the GeoIDs, while the GNRS maps from GeoID to network address. Here is an example of how Ncrs and the GNRS work together to support mobility. Here we have user James Fong in network who wants to register itself in network NE1. So it first sends a Ncrs insert to Ncrs, providing its certificate information. Then it sends a GNRS insert to the GNRS, providing its GeoID and network address binding. Later, it moves from network NE1 to NE2. So it needs to send a GNRS update, providing its new network address. Another user, Ncrs, wants to communicate with James Fong. So Ncrs first sends a Ncrs query asking for James Fong's GeoID. With the GeoID, Ncrs can query GNRS for James Fong's network address, with which these two users can communicate with each other. The Ncrs is not our focus, so here I would like to just highlight two basic functionalities of the Ncrs. The first one is NAND translation. So Ncrs provides a two-directional translation between human-readable keywords and GeoID. Also, it serves as a certificate registry, which is very similar to the public key infrastructure. To explore the weaknesses of the current GNRS protocol, we first identified 5 potential attacks. Then we provide our security countermeasures. The first attack we identified is GeoID spoofing attack. Here, a malicious user tries to bind another user's GeoID to its own network address, so it can direct another user's traffic to itself, causing denial of service to the victim. The second attack is stale mapping attack. In this case, the GNRS server is compromised and can purposely ignore the new GNRS update and still provides old mapping to other users who make a query. Therefore, the victim user will not receive any traffic from other users because no one else knows its current network address. The third attack is false announcement attack. Here, the adversary tries to bind its own GeoID to a different network address. Therefore, it can direct garbage traffic to the victim network, causing network resource consumption. A more sophisticated attack is collusion attack, which involves multiple protocol participants. For example, the mapping owner, its network, and the mapping storage location. All of them collude with each other and allow a fake mapping with false network address, pass all the verifications, and be stored as the mapping storage location. The last attack we identified is IP hole protocol attack. The dynamics in the IP space, known as BGP chum, may cause problems to the GNRS operations. For example, withdrawing IP prefix makes the GNRS mappings, the current AS hosts, become orphan mappings, and therefore we need to find a new mapping storage location to hold those mappings. The IP hop protocol in the GNRS is specially designed to handle these mapping migration operations. However, if we do not verify the mapping migration request carefully, an attacker may take advantage of our vulnerability and just send lots of garbage mapping to our victim network with the excuse of withdrawing our IP prefix. Before we go to the security solutions, I would like to first clarify our assumptions. First, this work is based on DMAP paper. We have two assumptions here. The first one is public key infrastructure, PKI. Also, we assume a clock synchronization system is available. There are three basic GNRS operations: insert, update, and query. Actually, the insert and update are quite similar. The insert can be considered as a first-time update. So here, we actually only need to investigate update protocol and the query protocol. The cryptographic algorithm we choose for the GeoID is elliptic curve because it's efficient. The security strength of 256 bits elliptic curve is comparable to 3072 bits long RSA. Now let's take a look at the GNRS update protocol. Here, the involved major network components are the mapping owner A is local router L, the border gateway router G, DHCP server D. The mapping will be stored as X in network NA2. The protocol flow is like this. First, A sends a GNRS mapping to its local router L, which then forwards the mapping to the border gateway router G. G verifies the network address in this mapping with DHCP server D. If the network address is correct, then G sends an ARC to L, which then sends another ARC back to A. This confirms that the update is accepted. At the same time, G forwards the update to X, and X replies with an ARC. That concludes the update protocol. All the messages here are carefully designed to prevent against the attacks we mentioned previously. So due to the time limitation, I won't go to explain each message details. Instead, I would like just to highlight those security countermeasures we introduced to prevent those attacks. Two timestamps, mapping generation time and expiration time, are added to prevent stale mapping attack. And to prevent GeoID spoofing attack, we require the mapping owner A sign this mapping with its private key, because only this user knows its private key, not others' private key. So A cannot pretend to be another user and use another user's private key to sign this mapping. Also, announce is added to prevent replay attack. Then to prevent false announcement attack, which involves a wrong network address, we set up two checkpoints. The first one is at local router L. When it receives a mapping update, L first check to see if the network address is correct or not. If it's correct, then L forwards the mapping to G. However, someone may ask, what if L is compromised and collude with the mapping owner A? To prevent that, we introduced a second checkpoint at G. So G verifies the network address with DHCP server D to see if it's correct or not. Then, someone may further ask, what if G is also compromised? It is less likely but possible. To prevent that, actually that is the collusion attack we discussed. So it involves mapping owner A, local router L, the border gateway router G, and the mapping storage location. So often colluding with each other and allow the fake mapping past the two checkpoints we just set up. So to prevent that type of attack, we require the border gateway router G also sign this mapping. Therefore, the final mapping stored as X is this one. So this mapping actually carries two signatures. The first one is from mapping owner A. The second one is from the border gateway router. Other users who make a query and obtain this mapping, they can verify with the Ncrs to see if the second signature really comes from the border gateway router of that network. This solution guarantees the network origin of this mapping, and therefore we can prevent a mapping attack against the mapping involves a wrong network address. So this is what we have done for the GNRS update protocol. And for the query protocol, the involved network components are user B, who wants to make a query, is border gateway router S, and the mapping is stored as X in network NA2. So the protocol flow is first B sends a query request to S, which then forwards the request to X. X replies to this request with the mapping B is asking for. Then S forwards this mapping to B. That concludes the query protocol. It is quite simple and straightforward. Also, here the message formats are carefully designed. And interestingly, we found out that if the GNRS update protocol is secured properly, there's not too much room for attackers to exploit in the query protocol. And to save time, I won't talk about the details in the query protocol, but if you are interested, you may take a look at my thesis. The last part of the GNRS security work is the IP hop protocol and its weakness. To cope with the dynamics in the IP space, in GNRS, the IP hop protocol specifies two operations, often mapping insert and mapping migration. Actually, these two operations are quite similar. Both of them involve moving mappings from one location to another. So here, let's take a look at the often mapping insert, for example. The protocol is like this. We have X in network NA2. Now it wants to withdraw its IP prefix. So X has to find a new mapping storage location to hold those mappings it currently has. That is Y in network NA4. So X sends the mapping to Y. Y accepts this mapping and replies an arc back to X. Okay, this is simple. But if we do not verify this mapping insert request carefully, there is a vulnerability. A malicious user, for example, E in network NA5, may create a lot of fake mappings and come to the victim, for example, Y in network NA4, say, hey, I'm going to withdraw my IP prefix. So I need to find a new place to hold those mappings that are currently stored as my location. And that's you. You should accept those mappings. Then, if Y does not do any verification and just accept those mappings blindly, first, it consumes its own network resource. Second, later it may provide those fake mappings to other users who make a query. So to prevent this attack, we ask Y run IP hop protocol to verify whether the mapping sender is really the legitimate storage location of those mappings. Because in GNRS to find the mapping storage location. We hash on the GeoID of the mapping, and the hash result will be mapped into a network address, which is the mapping storage location. Therefore, one can verify whether the mapping sender is really the legitimate storage location. If yes, then one accepts the mapping. Otherwise, it will reject. So that's the security solution we proposed for the orphan mapping insert. Now we have addressed the security issues in the GNRS. Then the next question is that, can we use the secured GNRS to extend security protection to the rest of the network? To answer that question, we look into putting access control as the GNRS. The result of that is the GNRS can serve both of security functions as well as some privacy functions. Particularly, as the GNRS, we've noticed that currently anyone can just come and ask for another user's GNRS mapping. For example, an attacker can come to GNRS and keep querying your GNRS mapping and obtain your mobility pattern from those mappings. That opens a door for attacks and exploits, and that is the issue we want to address. We believe that if we can restrict malicious access to the information that is needed to launch an attack, then we increase the difficulty for an attack to be launched. So to prevent information and the privacy leakage, we integrated the access control as the GNRS. And with the access control, we can do more than that. For example, we can support advanced services and fine-grained functionalities as the GNRS. The GNRS mapping can be granted based on where the courier is located and when he is at that location. If we have access control, we have to describe what it is we want to control access and how we control access to it. That requires a formal language to define the access control policy. In our work, we've used extensible access control markup language, and we integrated that into our access control framework. This figure illustrates our scheme. Here we have user A. He wants to tell the GNRS server S that I only want people to look me up if they meet such requirements. And here's my mapping, and here's my policy. Another user B comes to S asking for a mapping. S goes back to check A's policy. The policy can be whitelist, blacklist, or other forms of policy. And S, check, you do meet those requirements. So B, here's the mapping you're asking for. Or no, you don't, so you will not get the mapping. That lists the policy definition and categories. We investigated several different types of policy. The most basic one is this one, a specific GeoID with policy start time and end time. This policy is protected by A's signature. Also, we looked into whitelist and blacklist. Here, W stands for whitelist, B is blacklist, and the list of the policies is also protected by mapping owner A's signature. Further, we looked into two versions of spatio-temporal access control, which are closely related to the mobility. The first one is a general spatio-temporal access control, where the mapping is granted based on the location and the time characteristics of the courier. A more complicated version is a stateful spatio-temporal access control. Here, the mapping is granted based on not only the current location and the type characteristics of the query, but also its previous time and location features. Due to the time limitation, I won't go through the details, but again, you can look at my thesis for the details.
So before we go to the next slide, can you just say how do you trust, so temporal access, if you assume everyone has the synchronized clock, that's fairly straightforward. What was your strategy for trusting the spatial data, or spatial claims of the query?
Yes. Actually, we verify this location information with some trusted location service. So that's the one contribution of this work. And also, we define a state for the stateful access control, spatial-temporal access control. Basically, a state is the type and the location characteristics of this user. So basically, in the spatial-temporal access control with state transition, the policy is this user should be previously at some specific location and currently is in another specific location to gain this mapping. Actually, we propose a token approach to solve this state transition problem.
So if you were in a place at the right time, you acquired a token. And so then when you needed, you present that token as part of the protocol.
So that
you're
token
assuming a
is
trusted
approved.
location service.
Yeah, we had to assume a
extra
trusted
service. Okay.
Yeah.
Yes. So basically, the token is a proof of your previous type and the location. The next topic I would like to talk about is Internet of Things, IoT. This part of work is new and you might not have seen. So Internet of Things is a new trend and MobilityFirst would like to support it. Many current IoT systems cannot support applications seamlessly. A lot of legacy IoT systems are proprietary implementations, and it is very difficult to connect them and make them work together to provide seamless services to data consumers. This silo feature conflicts with the open spirit of the Internet and brings a lot of problems of interoperability and scalability. Therefore, people have proposed an overlay approach. In the overlay-based IoT architecture, standard control and the data APIs are introduced as the IoT gateway, which connects local IoT systems to the global Internet. Also, the IoT gateway publishes data to a central IoT server. This approach also has some problems. First, the merging of control and the data forwarding as the central IoT server is a bottleneck and brings scalability concerns. Also, the central IoT server is a single point of failure. And this architecture cannot support mobility very well, which is really a desirable feature we would like to have. Therefore, here at the WinLab, a unified IoT architecture based on MobilityFirst is proposed. And this architecture has 4 basic components. Here we have IoT devices, and this is IoT applications, the data consumers. At the bottom, we have MobilityFirst infrastructure. In the middle is Iot Middleware, which includes 3 layers. The bottom layer is the aggregator, which provides sensor abstraction to hide heterogeneous IoT hardware from the upper layer applications. And it also provides a single interface for data query and subscription. In the middle, we have LSG, Local Service Gateway, which connects the local IoT systems to the global internet. It also provides some basic measurements, such as name resolution, key measurement, and context processing. On the top, we have IoT service layer. This is a logically centralized server in the control plane. It manages subscription and also provides lookup service so that IoT applications can look up the IoT data and the service information. Now this figure illustrates how this architecture works. First, the aggregator collects data from sensors and forwards that data to the LSG. LSG can choose to store the data at some data storage location. Then it publishes the data to the IoT server. The IoT server can choose to enforce the access control as itself, or push it to the Ncrs or the GNRS. IoT applications can go to the IoT server asking for IoT data and the service information. With those information, the application can go to fetch the data, either from the data storage location or from the aggregator directly for real-time data. This architecture design takes advantage of the mobility-first infrastructure, especially the GeoID and the service layer. The use of GeoID facilitates device and the data retrieval. However, that also brings a new problem. As we have discussed previously, the GeoID serves as the network object identifier as well as the public key. That means it involves asymmetric crypto computations, which are too expensive for many low-end IoT devices. Therefore, in the local IoT system, the symmetric crypto algorithms are preferred. Then there's a gap between the globally used identifier GeoID and the locally used identifier or membership keys. How to bridge the gap without sacrificing security properties is our next task. And our solution is IoT Narrow Resolution Service, IoT NRS. It has 4 basic functions. The first function is GeoID assignment. So this IoT NRS assigns GeoID to IoT data, which is the major interest in IoT systems. But it can also assign GeoID to a specific IoT device if a data consumer has special interest in that device. Second, it serves as a local group authority to manage the local membership. Especially, it is responsible to establish a long-term membership identifier associated with a symmetric key with a new device as the device discovery stage. Third, it provides name translation between the GeoID and the local membership key. The last one, it provides key-related measurement, such as renewal key or revoke key. As we have seen, the GeoID is well defined and supported by the Ncrs and the GNRS. Then, how about the local membership key? How can we establish this long-term membership key between the new device and the IoT NRS with the guarantee of the authenticity and the integrity of this device? To answer that question, we developed a key provisioning protocol to establish such a long-term membership key. This part of work involves my intern work at Intel Labs, and we have a patent for this pending patent. Now we have two devices. The child device is a new IoT device who wants to join the local group, and the guardian device is the local group authority. For example, the IoT NRS in the MobilityFirst based IoT. And the result we want is a long-term membership key representing the mutual trust relationship between the child and the guardian. However, trust does not come from nowhere. If we want to build a new trust relationship, we have to extract it from an existing trust relationship. Therefore, to guarantee the authenticity and the integrity of this child, we need to introduce a third party as a trust reference. That is the parent. The parent serves as a trust anchor, and it shares a pre-existing trust relationship with the child device in terms of a parent key. Also, as the parent kicks in, we need to build a mutual trust dynamically between the guardian and the parent, so that later the parent can dedicate its privilege regarding to this child and help the child and the parent and the guardian to establish a new membership, new trust relationship, which is the parent, which is the membership key. So that's the logic why we change a two-party key exchange protocol into a three-party key exchange protocol. And now let me clarify our system model. Here we have three parties. The child is a low-end resource-constrained IoT device, and the guardian is the local group authority. They want to build a trust relationship in terms of a symmetric membership key. And the third party is the parent, which shares a pre-existing trust relationship with the child in terms of a symmetric parent key. But the parent cannot talk to the child directly. All the communications have to go through the guardian. Both the guardian and the parent are powerful enough to handle certificate processing or asymmetric computations. However, the child does not have such capability.
So in the context of IoT, can you clarify like what a parent device might be?
This parent device is the parent of the child. So for example, it can be the manufacturer of the child IoT device or the owner of the child device.
So it could either be the manufacturer's
Yes.
key server,
Yeah.
or it could be me, the owner of the child device. I run a key server for all my devices that I have,
Yes.
that I own. All right.
So wait, so in this model, right, there's a key server, then the guardian device is the access point that the child's talking to.
Yes, it's access point,
Gateway.
but also
Gateway
the
or something,
gateway.
yeah.
Yeah.
IoT gateway.
So basically, in this model, the parent will play the role of a server, and the child and the guardian are two peers. We look at this system model, and we realize the several challenges. First, the child device is a resource-constrained device, so it is unable to handle many heavy-duty tasks. Also, many IoT systems involve large-scale deployment, and hence they cannot be monitored or subject to complicated operations, for example, rekeying. And third, there is a dynamic trust establishment between the guardian and the parent. The last one, user-friendly because no IT professional should be required. Those challenges lead to our requirements for this protocol. First, scalability. We would like to support large-scale deployments. Dynamic mutual trust establishment and privilege delegation between the guardian and the parent. Also, we should conserve the consistency, which means all the three protocol participants should have consistent and correct view of this protocol session. We want to have secrecy and forward secrecy. That means the shared secret should be known only between the involved parties, and no third party should have information about this shared secret. Also, forward secrecy means even if a long-term membership key is compromised, all the previous communication sessions should not be in danger. As we are in the context of IoT, efficiency and lightweight are very important. Also, we would like average administration. That means no IT professionals are required. A key exchange protocol without a well-defined adversary model cannot be considered as secure and sophisticated. So here, I would like to summarize our threat model and assumptions. First, we assume a network adversary. That means the attacker can take full control of all the communication channels. The channel between the child and the guardian, as well as the channel between the guardian and the parent. It can modify the message, delete the message, replay the message. Also, we assume a weak software adversary. So that means the attacker can only access or override regular applications in the operating system, but it cannot access the secure storage, such as trusted execution environment, because we need a secure storage to hold the parent key. And there's no hardware adversary, so that the attacker cannot modify the hardware circuit. Last, we assume a trusted certification authority. That means we assume a public key infrastructure is available. We investigated several three-party key exchange protocols and decided to use Choose 3PKD protocol as one of the building blocks. This protocol has security proof, and there has been no identified attack against it. But still, we need to customize the Choose 3PKD protocol to fit into our settings, because the system model of 3PKD protocol is slightly different from ours. In Choose 3PKD, the KDC, Key Distribution Center, which is essentially a server, has direct communication channel with each of the two peers. Also, the two peers can talk to each other directly. However, in our setting, the parent, which plays the role of the server, cannot talk to the child directly. All the communications have to go through the guardian. Also, in 3PKD, there's no capability constraint for all the three parties. But in our setting, the child device is much less powerful than the other two parties, and it cannot handle many complicated heavy-duty computations. Someone may ask, why don't directly use Kerberos, which is a widely used three-party key exchange protocol? There are several problems with Kerberos in our setting. First, Kerberos has strict time requirements. Kerberos is a variant of needle shoulder. Some of you might familiar with the vulnerability of needle shoulder for replay attack. And Cobra's fix that vulnerability by introducing timestamps. That leads to the high requirement for the time synchronization. That means high accurate oscillators are necessary, but that is too expensive for many low-end IoT devices. Also, Cobra suffers from single-point failure. And another problem is that the Cobra runs at a KDC mode, which is not flexible and scalable enough for the heterogeneous parent device at a global scale. Think about the vast type and quality of child devices in the MobilityFirst based IoT architecture at a global scale. Correspondingly, the parent devices are also heterogeneous and numerous. One desirable feature we would like to have is to allow the child specify its parent to the guardian, so that the guardian knows who to contact for verification and authorization regarding to this child. But there's a problem with that. How can the guardian trust a third party told by the child? It is possible that the child and the third party parent collude with each other and cheat the guardian. Therefore, this leads to a need of authentication between the guardian and the parent before they actually go to the delegation and authorization. So that's why we introduced the Sigma protocol, a two-party authenticated key exchange protocol, to achieve the authentication. The Sigma protocol is based on Diffie-Hellman, and it uses certificates and the digital signature to achieve the authentication. It is the cryptographic basis for the IKE standard. Now let me summarize our contributions. First, we customized Chum's 3PKT protocol and the Sigma protocol to fit into our system model. The tricky part is that both of the two protocols are proven to be secure. However, combining them together is not necessarily secure. If we do not do this carefully, we may open a door for man-in-the-middle attack and replay attack. To overlay these two protocols together properly, we introduced the enhanced protocol context, which involves all the identifiers of the protocol participants as well as the nonces they contributed. That's the glue to stick these two protocols together, and I will show you later. Also, we performed security analysis. This protocol was initially designed for the device enrollment. However, it is also a general purpose protocol and has many use cases. For example, attestation, privilege delegation, and ownership transfer. Take ownership transfer for example. The parent may transfer its complete privilege over the child to the guardian, so that the guardian establishes a long-term membership key with the child, and that membership key becomes a new parent key to replace the old parent key, and the guardian becomes a new parent of the child.
So, are you going to go over this?
Yeah.
All right.
Now let's go to the meat, the protocol specifications. Here we have three parties: child, guardian, and parent. The key KK is the parent key, symmetric parent key between the child and the parent. G is the Diffie-Hellman modular between the guardian and the parent. It can be specified in the protocol specification, or we can also allow these two parties to negotiate. There is actually another round of message exchange before the protocol. In the MobilityFirst based IoT, the local group authority periodically sends out beacon, and new IoT device who wants to join the group replies to that beacon. But this round of message exchange is irrelevant to this secure key exchange protocol, so I just skip that. Now let's start the protocol. First, the guardian generates a fresh nonce and sends it to the child. The child also contributes a nonce and sends it in message 2 to the guardian. Also here, the child specifies which parent to contact for the verification. So that's very flexible. The guardian simply forwards message 2 as its own message 3 to the parent. So that's the first stage of our protocol, which corresponds to the first stage of 3PKD protocol. And all the messages here are in plain text without any protection. This is to reduce the overhead, but all the information will be confirmed in the following stage. Now the parent receives this delegation request, so it also contributes a nonce. Also, it generates its own Diffie-Hellman public component and sends this to the guardian as a Diffie-Hellman challenge. Now it's the guardian who first compute the expensive Diffie-Hellman shared secret. And in message 5, it sends its certificate and signature for authentication purpose. It also sends a proof of the successfully derivation of the Diffie-Hellman shared secret, which is the key AK here. So actually, this part uses AK to compute the authentication tag. The parent first verifies the identity of the guardian. If the parent decides to authorize privilege to the guardian and continue the protocol, it will generate a key material K, which will be used by the child and the guardian later to derive the final key agreement. And this K is sensitive, so it should be protected properly. Therefore, the parent generates 2 tokens to hold this key material, which is in the ciphertext. Also, these 2 tokens carries all the IDs and the nonces. That's the protocol context information. The token alpha is for the guardian, and therefore is protected by authenticated encryption using key EK, which is derived from the Diffie-Hellman shared secret. And token beta is for the child, so it's protected by the parent key KEK. Now, parent sends the tokens together with its certificate and the signature to the guardian. This message 6 overlays the Sigma protocol, which is the second stage of our protocol, as well as the second stage of the 3PKD protocol. So here, this part is actually the glue to stick these 2 protocols together. And the child and the guardian can verify the protocol context information carried in the token to see if they are working on the correct protocol session.
So I guess, well, I'm still confused. What if you had, in your attack model, could you have a child that was an attacker?
No, the child is the low-end IoT device.
Right, in that model you would have like a fake device, or this isn't
Yes,
supposed to
because
break that attack model.
this child device may be compromised.
Yeah.
So that the guardian needs to verify the authenticity and the integrity of this child device. Therefore, it needs to get help from the parent, because parent
Right,
has...
so all you have right now, okay, so maybe The only thing I see coming from the device is the IDG and the nods too.
This one?
Yeah.
Because,
So what keeps an attacker from spoofing those?
okay, so that's the key, KEK. So for example, if that KEK is a attestation key embedded into the child device by its manufacturer parent, the parent can actually verify whether this device is compromised with this KEK. So that's why this token is protected by the key KEK. So that's more hardware related operations actually.
So
Okay.
it's the KEK, right?
So, right, in the alpha and beta there, you're using the KEK?
Yes.
Okay. And then so later, when the device gets those, something about those.
If this
Great.
KEK is compromised, the child device, since now the guardian decrypts alpha for itself and forwards the beta to
Okay.
the child. So if the child device is compromised, then it will lose the key KEK. So it will be unable to decrypt the beta successfully. And therefore, it cannot get this secret key seed.
So you're assuming it can decrypt beta with the KEK?
Yes.
So the KEK in these next two steps, one will prove to the child that the parent is legitimate, and the other will prove to the parent that
Yes.
or to the guardian
Now-
that the child is legitimate.
Yeah, actually after message 7, both child and guardian have received shared key material from the parent. So that's the delegation. And if everything is correct, then these two parties can derive a shared secret successfully. But if there is anything, if there is any problem, then these two cannot derive a same key material at the end. Therefore, the last round of message exchange, message 8 and 9, are for confirmation purpose, so that both child and guardian know that the other party has successfully derived the shared secret key SK from the key seed K provided by the parent, as well as from the protocol context information, including all the IDs and the nonces. So this is the final output of the protocol key SK.
So the alpha gave the guardian the information needed for the guardian to check what the child gives back to the guardian in step 8.
Yes,
Which-
someone could certainly spoof message 2, but things would fail later on.
Things will fail in step
That will
8.
fail itself.
Yeah, because
7
we
and
have
8, yeah.
verifications in the following stages.
So like she mentioned Needham Schroeder earlier, it's the 4th and 5th step that finally closed the deal, where you finally prove that we went through all this work and yes, we really are who we say we are.
Yeah,
And often is how these
yeah.
things have to happen.
And also here, we instead of using time steps, we use nonces. So we don't require high accurate oscillators. And this protocol is a lightweight protocol for the child. The workload is shifted from the child to the guardian and the parent as much as possible. Also, the number of messages the child has to process is minimized.
How big is beta?
The beta, well, it depends on the length of the IDs and nonces. For example, the IDs can be 32 bytes, at least. Can,
Bytes?
yeah, or that's
pretty
too big,
huge.
so it can be 32 bits. I don't remember exactly the numbers, the length we used in the prototype. And for the nonce, for the prototype, I think we only need, we tried 256. And also here, PS is local message information that specify the by the guardian, so that the parent actually does not know this part. And this part will also contribute to the final key, SK, so that this key actually is only known between the child and the guardian. The parent has no idea about this key if this part is introduced
Well,
by
I was
the
just-
child.
I was
or by
trying to
the
get an
guardian.
idea of the order of magnitude of the things you're sending around, so it looked like
Here, for
tens to low hundreds of bytes.
yeah,
Oh, for your hashing, so 128 bytes.
yeah. So for example,
160
the
by
hash, yeah, the hash then is for the hash function we use SHA-256, so the output is 256 bits. Bytes. Bytes. We implemented a prototype to prove our protocol design. We adopted a modularized approach for the software framework. And for the underlying protocol, underlying crypto library, we investigated two lightweight embedded SSL libraries, Embed SSL and WAF SSL. We implemented two sets of the crypto wrappers for both of the libraries. And at the point of the prototype implementation, we found out that the Embed SSL was more robust and more user-friendly. So we actually integrated Embed SSL and its crypto wrapper into our final prototype. And here is our choice for the crypto algorithms used in the protocol design. This is the software framework for the prototype. Each party has three basic components. The instance manager creates a protocol instance of a corresponding party as the device and then performs configurations. The protocol manager manages all the sessions of our protocol instance. And the last component is the utility functions. We implemented this and have here is the demo output of the prototype. This is the parent, the child, and the guardian. All the message exchange steps and the major operations are printed out. And at the end here, we can see the child and the guardian have reached a key agreement, which is this one, key. And also, the key ID is basically the hash of the concatenations of all the identifiers and the nonces involved. And this ID uniquely identifies this protocol session and binds to the key. Okay, to conclude my talk, first I would like to summarize the thesis contributions. First, we investigated the GNRS protocol, identified several attacks, and provided countermeasures to solve those problems. Also, we integrated the access control framework as the GNRS. Third, unified MobilityFirst based IoT architecture is presented with the focus on the NAND framework. We also developed a lightweight key provisioning protocol for the device enrollment, but this is also a general purpose protocol. Last, this thesis also explored a lightweight overlay tunneling approach as a policy tool to defend MANETs, but due to the time limitation, I didn't discuss this work in the talk. As for the future work, network infrastructure without any security protection is untrustworthy and therefore cannot convince users to adopt such a system. So it is important to actually implement and integrate the security solutions we proposed for the GNRS into the MobilityFirst prototype And then we can perform a complete and faithful performance evaluation. Also, the Ncrs is very important in the MobilityFirst. However, only the basic functionalities of the Ncrs have been defined so far. And the next step will be develop the Ncrs protocols and the specifications. Last, routing is also a critical component in a network infrastructure. In MobilityFirst, we have intra-domain routing protocol G* and inter-domain routing protocol EIR. Both of them need proper secure protections. Especially, we have already identified several attacks against the G* involving the use of in-network storage. So it's important for us to propose security countermeasures to prevent those attacks. And this is a list of my publications, including a pending paper and a pending patent. Okay, thanks everyone for attending my thesis. And special thanks to my advisor. Without his support, this thesis cannot become true. I feel so lucky to have such a wonderful advisor. Thank you.
She says it right now, but she hasn't had the closed session, so. Any questions from the audience?